This video is on the objective solve factorable trigonometric equations in quadratic form. And this is the second video on this. Hopefully you've watched my first one. And let's just take a look at the question I'm given. So yeah, if you want to see how they're doing things, how they're instructing you, click on more instruction. Look at their videos, their notes, their examples. Hopefully those help. Alright, so this is another one where there's tangent involved. The first video in this objective I did also had tangent involved. Just know that it's not always going to be tangent. Alright. Might be sine, cosine, secant, might be some other function involved instead of just tangent. Please know that. Alright, so we're asked to solve the equation for beta. And so there's 5 times the tangent of beta squared plus 5 times the tangent of beta equals 0. And they only want the values of beta, though, that are solution, make this true. They only want the values of beta that are between negative pi and positive pi. All right, but not including positive pi. All right, so write this on some paper here. So again, we have this equation: 5 times the tangent of beta squared plus 5 times the tangent of beta, and it's already set up the way I want, where everything's on one side and zero's on the other. Alright, you got the this is like a quadratic expression over here, the highest power of the unknown, which is tangent of beta here. The highest power you're seeing on that unknown is 2. Now, I mentioned this last video as well. If you want, just to save some writing, like I mentioned, our unknown here is the tangent of beta, and we'll eventually be solving for beta. So if you'd like, we can substitute some letter for this, like x or something, right? So say everywhere I see tangent of beta, I just replace it with x. So now I'm looking at 5 times, and then instead of the tangent of beta squared, it's x squared. Plus 5 times, and then there's another tangent of beta. Place that with x as well. And then we have basically like it's a quadratic polynomial equation now. And it's already set up the way I want, the polynomial on one side, 0 on the other. So then we take that polynomial on this side and we're going to factor it completely. Now, I'm not, last time there was a difference, the first video I did on this objective, there was a difference of squares involved. This one doesn't really have that much to do, but hopefully you remember all your factoring techniques, because I'm not going to go into all those. You should know those already, or at least be able to review them from pre-calc 1 or some previous algebra class you've taken. Alright, so I'm going to factor this polynomial completely. Now, the first thing you do when factoring is pull out the greatest common factor of all the terms. Now notice that both of these have 5 times x, right? 5 and a factor of x in common. And then if you pull out a factor of 5 and a factor of x, what's left over would be x plus 1. Right? If you were to redistribute the 5x, you'd get that back, right? And I have what I want now. I have a product equal to 0. So then I'm going to apply that 0 product property that was mentioned in the first video. Right? That's if a product is equal to 0, then one of the factors is 0. So either 5 is equal to 0, but that can't be true, right? So you're not gonna get anything from that. So either 5 equals 0, can't happen, or the value of x is 0, right, this other factor, or the value of x plus 1, this third factor, is equal to 0. All right. And then solving for x here, we get, the value of x is either 0 or the value of x is -1. Right. But this isn't what I want. Right, this is just one step in the process. My original equation, I'm trying to solve for beta, not x. So we need to substitute back, right? So now that I've solved for my substitution variable, we need to substitute back and solve for my original variable beta. All right, and when I substitute back, I'm going to be getting the two linear equations in tangent. And hopefully you recall a previous assignment where you were asked to solve linear equations. So I'm going to be doing that, right? Now remember, every time I see x, that was the tangent of beta. So either the tangent of beta equals 0 or the tangent of beta equals -1. And I have to solve both of these, all right? Find values of beta that satisfy both. So I'm going to start with this one. All right, let's solve the tangent of beta equals 0. All right, so when did that happen? All right, when was the, now again, this is a linear function, a linear equation in tangent. Got the tangent alone. So all I need to do now is just think once around the unit circle. Just think once around the unit circle. What was an angle? Starting from 0 going to 2 pi. What was an angle that had what were angles that had a tangent of 0? Well, this beta then, right? The beta is the angle. 0 had a tangent of 0, right? The tangent of 0 radians was 0. So 0, right, let's make that a little thicker. And if I just go around add 2 pi, subtract 2 pi, if I add any multiple of 2 pi, say 2 pi times k, where k is some integer, I'd get another angle that has a tangent of 0. But that's not the only one, right? 0 isn't the only angle going once around that has a tangent of 0. So does pi, right? The tangent of pi, if I go halfway around, the tangent of pi also is 0. And from pi, I could again add 2 pi, subtract 2 pi, add any multiple of 2 pi. All right, so add 2 pi k, where k is an integer, and I'm getting another solution to this equation. Now I could have put both of these together and just said that beta is some multiple of pi. Alright, because here you're getting 0, here you're getting pi, here you're getting 2 pi, here you're getting 3 pi, 4 pi, 5 pi, 6 pi, 7 pi, 8 pi, 9 pi. You're getting all the multiples of pi have a tangent of 0. So we could have also just said this. Right? Now if I list some solutions to this, right? I'm going to do a list of, if obviously 0 is a solution. And then going this direction, because it's k times pi here, I'm just going to be adding pi. And going in this direction, I'm just going to be subtracting pi. So like I said, pi is a solution, 2 pi is a solution, 3 pi is a solution, etc. And then negative pi would be a solution, negative 2 pi would be a solution, and so on. But they don't want all these solutions. Right? They only want ones. They only want values of beta, but in this range, right? We want this. We want negative pi less than or equal to beta less than pi. So they want values of beta from negative pi to pi, but not including pi. So looking at my list of solutions here, the only ones that satisfy this are negative pi, right? Negative pi is included here, and 0. Right? 0's in there as well. Pi is not, right? This is strictly less than pi. So the only two solutions I'm getting out of this first equation are beta equals 0 and beta equals negative pi. All right. Now that was the first equation. We got now let's look at this other one. Now the tangent of, so 2, when is the tangent of beta equal to negative 1? So again, I think once around the unit circle, and I think I did the same equation in the first video on this objective. And the angles that have a tangent of negative 1 would be 3 pi over 4 in quadrant 2 here, and also 7 pi over 4, but notice that these are just pi away. Remember the period of tangent is pi. So if I took 3 pi over 4 and just kept adding pi, I'd get other angles that also have a tangent of negative 1. So I'm just going to write plus pi k here, right? Just because the period of tangent is pi. All right, so 3 pi over 4 and then plus pi would be 7 pi over 4. That also has a tangent of negative 1, then plus pi again, minus pi, whatever. Just adding and subtracting multiples of pi would give me another angle with a tangent of negative 1. So here's a description of all the solutions to that equation. And then I'll list some. All right, so again, 3 pi over 4 is a solution. And then going this way, I'm just going to be adding pi, which is 4 pi over 4. All right, getting a common denominator. And then going this way, I'm going to be subtracting pi. So 7 pi over 4 is a solution. 11 pi over 4 is another solution, and so on. Subtracting pi, get negative pi over 4 is a solution. Negative 5 pi over 4 is a solution. And again, I could do that all day long. But they want they want values of beta in this range, right? From negative pi to pi. So the only ones that actually are satisfying that range there are these two. All right, negative pi over 4 is in here. 3 pi over 4 is in here. All these are too big. These are too small. All right, so all together, the solutions they want, the solutions that I'm going to be typing in, are these two and these two. All right, I'm going to put them in order from least to greatest. So negative pi, then negative pi over 4, then 0, and then positive 3 pi over 4. All right, so here's what I'm going to be typing in, right? The only solutions that actually are in the range that they asked for. Okay? All right, so back here, typing those in. So first, negative pi, and then separated by commas, right? So comma, then negative pi over 4, comma, 0 for beta is a solution, comma, and then 3 pi over 4. And that's it, those 4 numbers. Hooray. All right. So notice again, they didn't substitute x for tangent beta or y or whatever you want, and you don't have to. I mean, you can factor these trigonometric expressions. You can factor them just like polynomials and leave it as tangent beta. I don't know. I just do substitutions sometimes just so I don't have to keep writing tangent beta all the time. Or secant beta or sine beta or whatever the trig function is. You don't have to keep writing it over and over again. You just write a single letter, and then once you solve for that substitution variable, then you substitute back and solve for the original variable, like I did here. Alright, so hopefully watching me do this, or looking at the more instruction, or reading the answer explanations when you see them, hopefully all this stuff helps you when you work on this material on your own. And thanks for watching.